Welcome back, everybody, to the next part in the series about building a simple or the simplest neural network possible. So the idea of this series was to first introduce the topic, get an idea for what those spaghetti diagrams that we constantly see are. So what are those circles and what are those arrows that point to the circles? See the introduction for that information. And then the next part was to build, in this case, a simple neural network, which means just fitting a line through these dots you see on the screen here. And so these dots are temperature on the x-axis, relative humidity on the y-axis, and we're just basically trying to fit that target line, that blue line you see there, and that black line is what our neural network is doing. So it's actually running through right now, I have it actively running, and what we saw in the last video was this was kind of taking forever. So that black line is slowly making progress, slowly tilting, and eventually after a long time, I think it took me like 10 minutes or more for this black line to finally lay right on top of the blue line. But the point is it does converge. Now, our problem, of course, is that doesn't make any sense. That takes forever. Why does it take forever? One, and the second question is, well, how can we make it go faster? And so this is a technique you've probably already seen in neural networks, but let's dive into it here. So I'm going to kill this for now and show what happens when we try to increase the learning rate. So one thing that we talked about in the last video too was the learning rate. So the way that the neural network is learning that line, that to fit that line, is it's slowly changing and updating the slope and the intercept. So those are the two things that we need to change, and the neural network is trying to learn using the data. And the way it learns that is through these derivatives. And we spoke about it very briefly, and we didn't go into much detail. But this is the change in error with respect to the slope. So that's the velocity. That's how fast, how far off I am essentially from my answer. And the learning rate is a way to sort of tamp that down, to slow down so you don't overstep. And so what would happen, and I think I showed this in the last video, was if you increase this learning rate, so we had it at 0.001, if we decrease that to 0.01 instead, what we get is completely missing the answer. And you can see it here because what happens with the error, and this is what I'm printing here, are the maximum error and the mean squared error down at the bottom there. What's happening is that you've jumped completely over the answer you want to get for the slope and the intercept, and you're approaching infinity. So that's wrong, and you don't want to do that. The way around that is, well, we want to keep a high learning rate, but how do we make it so it doesn't overshoot our answer? And you've probably seen this in previous videos, but the way to do that is through normalization. And so what normalization means is, instead of you having, let's go ahead and plot this again so we can see. Instead of having something that has instead of your x and y variables having a range from, in our case, like -15 in temperature to 30 degrees Celsius, and relative humidity from 0 to 100% relative humidity, you scale that down. So that way your variance, or your standard deviation in this case, also variance, scales down to 1, and your mean is at 0. And so this is called standard scaling, and that just sort of squishes your data set down. So let's do that real quick for both the x and the y. All right, so what we do is we find the x mean, x standard deviation. All right, y mean, taking that y real, excuse me, y standard deviation. And really what's amazing about this is that it actually works. Like doing something so simple as what I'm about to do, which is just scale the x and y variables, works really surprisingly well. And you'll see what I mean in a second, for allowing you some flexibility with the learning rate, and allowing that learning rate to be a little bit, to go a little faster. All right, so here's the basic thing here. Actually, let's write a quick function also if we wanted to go back to the real relative humidity and the real temperature values. So what we do here is let's call it go back function, and you're going to pass it a variable. I'll call it z just so that I don't mix it up, and z mean and z standard deviation. That way I don't mix it up with the x and y variables we already have. So all you do is reverse this equation up here so that you resolve for your original x value or y value, whichever one you want to go back with. And we're going to be going back with the y value, as you'll see. So that is z times the standard deviation times z standard deviation. I'll just come up with a better name than z. That's kind of lame. In any case, there's my go back function. We're going to use that later. But before we use these to actually train the neural network, I want to just show you what they look like. That way we at least have a concept of what's going on. So let's go ahead and copy all this guy and run it interactively. There we go. Boom. All right, and we'll look at two things. First, we'll look at the distribution. So I'm just going to look at the distributions of x. What does that look like? There it is. So there is our normalized x, right? The mean is roughly over here. Well, that's a little weird, but okay, the mean is roughly there. I think it might be because of the bin sizes I chose, but in any case, the mean is supposed to be at 0, and the standard deviation is scaled down to 1. So that's what this means. So that's x. We can take a look at y as well. And really shout out to Seaborn for being so awesome. I mean, look at this. Just to create a distribution plot, that's all you had to do was type in SNS dist plot and then type in the variable you wanted. You could also add the number of bins you want as well. So as you can see, though, our relative humidity and our temperatures are both scaled to have a mean of 0 and a standard deviation of 1. Perfect. All right. So now what this means for, actually let's do it this way. Yeah. What this means here is everything is going to stay the same as far as our code goes, except for the last little bit where we actually want to plot what's happening. So this is where we're going to apply this go back. So this is predicting a y. So now that we're updating that slope and that intercept and using our x value, we want to go back to a realistic relative humidity value, one that goes from 0 to 100%. So real units. So this means that we're going to take that y mean and y standard deviation and just plug them into our go back equation here and let the thing run and see what it looks like. So let's cancel out of this interactive shell and just run the code. Let's go. Boom. See how fast that goes. And as you can see, it's not blowing up and it's converging a lot faster on the line. I mean, to me, this is so remarkable that something so simple can allow you to accelerate learning so quickly. And all we did was take that data set and normalize it, do the standard scaling as you just saw. Barely did anything else. The other thing to note here is that we could actually bump this learning rate up a lot higher as well for our linear system. And again, it's just going to go a lot faster. So let's try that. And go ahead and play around with that. I mean, this is the whole point of the building blocks. Once you understand the basic building blocks, you can play around and see just how much of these other concepts that we've seen or read in the literature, what they actually mean. And I think this is the real power of dealing with a simple model like this. So you can see like it converged really quickly onto our value here. And look at our errors, they're barely changing, which means you're right on target. All right, perfect. One last thing, we looked at the learning rate. Excuse me. But now what happens if you initialize the intercept and the slope to something larger? What would that look like? And you can see, you can ask the question, well, will this still converge if I started from an initial guess? If I thought my intercept was at 60, but I've normalized my data, will I still get to the answer that I'm interested in? Valid question. Let's see. Save that. Run it. Let's take a look. I don't see anything yet. But hey, look at that. The thing just emerged out of nowhere and just gently landed on the line that we're after. I mean, again, that's pretty cool, I think. All right, let's kill this. So hopefully by now we've gone through the basic building blocks and we understand something about the concept of what it means to change the error over time. So how do you update the slope and the intercept? What are the actual variables that are involved? So the things that we're trying to predict, the neural network is trying to predict, oftentimes are called parameters. And those parameters are the slope and the intercept. And usually what is also done and what's not done in this really simple example that I've walked through here is there's an activation function. And that activation function just takes these equations and instead of it being linear, they'll wrap it in some other function like a sigmoid here. Some way to take this and make it nonlinear. So right now we were trying to do an equation for a line, linear, we're fine. If you're trying to do something more complicated and you added a few more nodes, you would add a function potentially like the sigmoid function to try to capture any weird nonlinearities in your data. We're not going to do that here, but if you'd like to see that video, just hit me up in the comments. I'd be happy to do one where we add this sigmoid layer. But instead, I think it's more helpful to go now to the more practical example of doing something with Keras. So for those of you who don't know, Keras is like this really simple way to do what I've just done here and even build even more complex deep learning and neural network models with a few lines of code. So we're going to build a linear model with Keras, and then we're going to try to add a little bit more data in here, pull it from the US Climate Reference Network, pull a ton more data, and see if we can't do some other fun mapping exercises that are a little bit more deep learning like. This is clearly not deep learning, this is just fitting a line. There's much smarter ways to fitting a line. As you probably saw, the seaborn library uses a much smarter way for fitting a line than a neural network. And in this case, we're trying to understand the building blocks, so we fit a line. So stay tuned for the next episode where we talk about Keras. And if you want to know more about the actual math behind this change in error with respect to slope, just ask me in the comments and I'd be happy to make another video about that. So thank you, and I'll see you in the next video.